Hello. In this video, I'll go over the questions in exercise 12E on trigonometric equations. In question 1, we'll be looking for answers that are within negative 180 to 180 degrees. So let's begin. First of all, let's find out what the reference angle will be by undoing this ratio. And cosine will take on negative root 3 over 2 when it is 30 degrees. And I know that cosine would be positive in quadrant 1 and 4. So the second answer will be 360 minus 30, which is 330 degrees. Maybe actually let's move this up here. And this originally has a period of 360 degrees. Now if I divide everything by 2, I should have two particular answers followed by what I can add and subtract to each of these angles. And I notice that if I subtract the first one by 180, this will still be acceptable. Whereas if I take 165 degrees and subtract by 180, that's also within the domain of negative 180 to 180 degrees. And those are our four angles. B, let's find out what the reference angle is. It's actually the same as the last time. So we can go ahead and just write down 30 degrees again. And for the fourth quadrant answer will be 360 minus, so again is 330 degrees. Original period will be 360 degrees. Now I'm going to divide everything by 3 this time, including the period. So now we just have to keep adding or subtracting multiples of 120 and generates the rest of the angles. So if I take 10 degrees and minus 120, this is acceptable. If I take 10 degrees and plus 120, that is also acceptable. So let's go ahead and write down the second solution. We can minus 120 degrees, or we can add 120 degrees, but this will be above. So therefore, we will only have 5 solutions. So let's take that away. I seem to be forgetting one answer. And it's, sorry, I could also subtract this by 120 further. I didn't go all the way back. So there are our 6 answers. Now, part C is actually quite similar to what we've done before, except there is an extra step or 2 in order to isolate the ratio first. So now let's go ahead and undo the cosine. So we want positive, right? So therefore 1 quadrants 1 and 4 once again. And cosine is 1/2 when it is 60 degrees. The other angle will be 360 minus, so 300. Original period is 360 degrees. Dividing everything by 2. The new period will be 120 degrees. So we're going to add and subtract until we got all the angles. So let's just go backwards first from 20. If I subtract 120, I will have minus 100. Minus another 120, that falls below negative 180. So let's go up instead. 20 plus 120 will be 140. And if I go 120 more, it's 260, so that's above. And then let's start with 100 degree angle. Go back one cycle, we have negative 20. Go back another, and we stop. The next one will be negative 260, too small. And then if I go from 100 degrees and up by 120, that's too big. So we can stop here. Again, we will have 6 solutions. So tangent, let's isolate. So let's undo the tangent ratio. Now we have -1 here. So -1 basically just tells us that it will be in the, so let me take away the negative and write down what those quadrant's answers should be. Tangent is negative at quadrant 2 and quadrant 4. So basically that's our reference angle. So I can't really write down what this is, but I could use it to help us find out what the angles has to be. So this is going to give us, so maybe as an aside, I can write down the reference angle. Okay, so if the reference angle equals 45 degrees, so I will take that 45 degrees and do 180 minus that, as well as 360 minus that, right? Because I want the angles in the second and the fourth quadrant. But tangent is kind of nice because I could actually just group these two angles together and write down one of the answers with the original period to be 180 degrees. So this is vastly different than sine and cosine. You know, for sine and cosine, we will actually have to write it like this, and then we do plus minus 360 degrees of multiples of these, right? But because tangents actually have a smaller period, and we can actually group all the solutions by just collecting them with one particular solutions and generating them with periods of 180. So that will simplify things a little bit. So now I will have to multiply everything by 2. And that includes the original period for tangent. So you see that this number here, it's not in the domain. So what I have to do is I have to subtract 360 to get to 90 degrees. And if I go 360 degrees one more time, that will be below -180 degrees. So there's only one answer in this question. Question 2 is expressing your answers in radians, and it's only between 0 to 2 pi. So let's go. Let's undo the sine ratio. So I know sine will be positive in quadrants 1 and 2. So we can go ahead and write down what that reference angle is. And that is, so this is in radians. I know that in degrees it will be 60 degrees. So I can do pi by 3. That's the angle in quadrant 1. In quadrant 2, it will be pi minus pi by 3, which gives us 2 pi by 3. The original period will be 2 pi n. So let's divide everything by 3, including this period here. Now, it's not very friendly to actually add something that's over 9 to something that's over 3 as fractions. So what I'm going to do here is I'm going to replace this as 9 pi, 6 pi over 9. Okay, because 2 pi over 3 is 6 pi over 9. So now I can add and subtract with ease. So let's do that. We have pi by 9 as one of the angle. And if I go back one turn, one cycle, it will be minus 6 pi on the top. So it becomes minus 5 pi over 9. And I could also do another spin. Now, when do I stop? Well, actually, because this is a 0, so I shouldn't even need to have these two solutions. So any negative solutions, it's not good enough. So now let's go up instead. Let's add 6 pi by 9 to pi by 9. So give us 7 pi by 9. And then we can do that again. And then we can do that again. But if you look at this number, this is actually above 2 pi. So how can we spot this easily? Well, Since all of these angles is in terms of something over 9, then maybe I can just change this to 18 pi over 9 so that I know when to stop for the denominator. And then here you see that 19 is definitely bigger than 18, so this falls outside the domain. So we are done for the first particular solution. Let's do with the second one. So let's generate the other angles from 2 pi by 9. Now we know that we can't go backwards anymore. If I minus 6 pi, that will fall below 0. So let's just go up one cycle. And if I do that once again, I get 14 pi by 9. And then if I do it once again, this will be 20 pi by 9, but 20 is bigger than 18, so we erase that. And that will leave us with our 4 solutions. 6 solutions, I cannot count. Okay, so let's isolate cosine 3 theta, undo cosine. This is a special case. Cosine is negative. Cosine is 1. So if you actually sketch the unit circle, cosine is 1 at 0. So this is 3 theta equal to 0. Original period will be 2 pi. So if I divide everything by 3, I also divide this by 3. So I'm just going to keep adding 2 pi by 3 until it goes above 2 pi. So therefore, this will be 0, 2 pi by 3, 4 pi by 3, 6 pi by 3. But you notice that 6 pi by 3 is exactly 2 pi. So we could just write down 2 pi. Do we need to go further? No, we don't, because 2 pi is the endpoint. Okay, one tempting thing to do is to multiply both sides by 2 and just write it as this. Nope, can't do that. So what you must do is, first of all, undo the sign ratio. Okay, root 2 over 2 is actually the same as 1 over root 2. So for those of you who memorize that as 1 over root 2, this is 45 degrees, which is pi by 4 in radian. Now sine is positive in both quadrants 1 and 2. So the second answer will be pi minus this reference angle, which gives us 3 pi by 4. Original period is 2 pi. So after multiplying everything by 2, I'm going to add or subtract multiples of 4 pi's, which I can write as 8 over 2. Okay, so I'm just adding, subtracting 8 pi over 2. I can't go backwards, otherwise it will be less than 0. So let's go up once. But notice that 9 pi by 2, okay? 9 pi by 2 is actually 4.5 pi, which is bigger than 2 pi. So actually, we can't even go up here. What about 3 pi by 2? If I go backwards, 8 pi, it will be negative 5 pi, so no good. And if I add 8 pi to 3 pi, it becomes 11 pi. And that's also no good. So those are the only 2 answers. And here, we will isolate the sine square. And then we can square root both sides and just have what sine square is. You could also do this by changing this to cosine, but does it actually make it any simpler? Actually, it would. So I'm going to show you both ways. Let's just solve it in terms of sine. So if I take the square root of both sides, this will be plus or minus 1. So we actually have 2 cases. So let's split that. We have sine 2 theta equals over 3 equals 1, or Sine 2 theta over 3 equals negative 1. So when I undo sine, actually for both sides it's the same. But here I know that we have a reference angle that is the same as before. No, I would like to do it this way because sine of this particular solution is on the borderline. So if you sketch the unit circle, when it's sine negative 1, it's at this point down here. So this is at 3 pi by 2. So I wanted to do this 0 and negative 1 when the angle is 3 pi by 2. So for positive 1, it will be at pi by 2. So here I will look for the reference angle because I will just be doing more. So here on the left, this happens at pi by 2. And then we have the period to be plus minus multiples of 2 pi. We don't have a secondary answer here because this only occurs once in a cycle. And then maybe I'll just finish the left-hand side first. And we are going to multiply everything by the reciprocal. So we can multiply this by 3 over 2 to cancel out the coefficient on the left. And likewise, if I multiply this by 3 over 2, it becomes 3 pi n. And if you notice, I cannot actually minus this by 3 pi because it will be negative. And if I add 3 pi, it's way bigger than 2 pi, right? So on the right-hand side, we have something very similar. This angle is 3 pi by 2. So then again, we can multiply both sides by 3 over 2 to give it a coefficient. We'll just write down the period and the new period as well. So this will be 9 pi by 2. Now this is not a viable solution because this is bigger than 2. That's 4.5 pi, which is bigger than 2 pi. So we actually have to go back one step. So 9 pi over 2 minus the 3 pi, it's going to give us 3 pi by 2. And if you try to go back again, it will be negative. So that's no good. Actually, these are supposed to be pi by 4. Let me change that. This is 9 pi by 4. It's just my calculation mistake. So now if I go back, so 9 pi by 4, in this case, it will be 2.25 pi. It's still too big. So if I subtract, what I mean is if I subtract 3 pi here, this will be the same as 9 pi, 12 pi over 4, which is negative 3 pi. So you notice that it will never, okay, here there is actually no solutions, despite having a particular solution. It's just that it will never fall in that domain. So our only solution is this here. Only solution is 3 pi by 4. Now, how can I do this? By using a trig identity. We can use the fact that this is, so cosine square x equals 1 minus sine square x. Or likewise, sine square x equals 1 minus cosine square x. So let's use the second form. So if I replace this with this here, I will have negative cosine square 2 theta equals 0. Therefore, cosine square of that equals 0. And if you square root it, notice that this will be plus minus 0, which is still 0, right? So let's just write one extra step. Then if I undo cosine, when is cosine 0? when it's pi by 2, right? So then the original period will be plus minus 2 pi n. And then we can go ahead and multiply the reciprocal of the left-hand side to give us this particular solution, and this to be our new period. So if you try to minus the 3 pi, that's way too small. And if you add 3 pi here, this will become 15 pi over 4, which is a little bit less than 4 pi, but it's way bigger than 2 pi. So therefore, this is the only solution. So here it's nice because there's only one case to consider rather than two cases in the sign on the left. And that's it. Hope you guys learned something. See you in my next video.